hello, I'm David from Georgia Tech, and I'm presenting VillainNet, targeting poison attacks against supernets along the accuracy latency forever frontier. So super networks are a special type of neural network that essentially you train once and you can get a whole bunch of different subnetworks from it for varying deployment conditions. So for example, we can take this one super network and we can get a large subnetwork that has high accuracy, high latency. We can get a medium subnetwork that has medium accuracy, medium latency. And then we can get a small subnetwork that has low accuracy and low latency. This could be useful in the sense of like a self-driving car, for example, where we want to change the latency of the model depending on the speed of the car or depending on the weather conditions. So for example, in the rain where where the vision might be obscured, we might want to choose the model that's the most accurate. So we would choose something that's the highest accuracy, the highest latency. Then in better weather, we would choose something that's medium. And then finally, in perfect visibility, we would choose something that makes the fastest decision making. These three choices actually exist along a range of potential options, and these super networks can be comprised of up to 10 to the 19th potential subnetworks. So you can imagine how just these three are just a very small subset of the ones you can potentially choose for a use case. So now let's consider an attacker who is aware of this kind of supernet usage. So let's say they want to attack a self-driving car utilizing this supernet. So they want the car to kind of come upon a merge sign that has some sort of backdoor or a pattern on it. The self-driving car driver or the person in the car is unaware that attackers have actually backdoored that car. Importantly, the attackers want the attack to only operate under a specific deployment condition. So in this case, they want it to be under, let's say, 75 miles per hour in sunny weather. Importantly, this corresponds to some real-world activatable condition. So in this case, the car will not see the merge sign correctly and will go ahead and see it as, let's say, a speed limit sign, go forward, and crash. But how does the attacker actually do something like this? So if the attacker tried to use a traditional poisoning approach, which there's plenty of prior work that does this, they might want to, let's say, create a poison data set. They might select the subnetwork that they want to target, corresponding to whatever condition they want. Then they might fine-tune that subnetwork on the poison data, deploy the model to the car, and then finally expect some sort of car crash. What would happen was, yes, the car would crash, but in reality, it would be incredibly easy to detect because, as you'll see in a second, when they do it this way, the attack is detectable through any subnetwork that would be sampled. So this means that if an investigator were to try to test the super network for some sort of backdoor, they would easily find it and then prevent the crash in any future scenario. So to visualize this scenario, we have this graph which shows the accuracy and the attack success rate for each subnetwork of the super network. This is 1,000 sampled. So the orange points represent the accuracy on poison data, so the attack success rate, and then blue points represent the subnetwork accuracy on clean data. So you can see that for every single subnetwork has a high attack success rate, which is not ideal and doesn't correspond to the attacker's goal. And that means that in the case of an investigator, they could easily sample a single subnetwork and detect that the attack occurred. Right. So this led us into VillainNet, which gets around this kind of problem. So VillainNet takes as input the supernetwork and some sort of target subnetwork configuration. VillainNet first does subnetwork batch sampling, so we sample, let's say, 8 to 16 random subnetworks. Then we calculate a distance to target calculation for the target to these randomly sampled ones. So ideally, the farther subnetworks should be affected by the poisoning, and farther subnetworks should be less affected by poisoning, and the closer ones should be more affected. Right? But how do we actually do this, calculate this distance between subnetworks? Well, intuitively, the supernetwork kind of gives us an easy way to do this in a few different ways. So the first way, we might want to take that flop range we saw before and kind of just subtract the distance between the two subnetworks on the flop range. Right? So in this case, we would have 122 megaflops between the two subnetworks. In a different case, we would use the edit distance for the architectures. So these two subnetworks would have, let's say, a specific width and a specific depth. We could calculate the edit distance between those architectures. And then finally, we might want to use the shared parameter distance between them. So since this super network is entirely weight shared, we might want to calculate the overlap in the parameters used between each subnetwork. So in this case, we can see that those overlap, and we can calculate, let's say, this shared parameters. This is a made-up number, but conceptually that applies, right? So these are all normalized to be between 0 and 1. So in the case of the flops distance, for example, we would scale it between 0 and 1 based on the maximum flop distance, right? So between the minimum subnetwork and the maximum subnetwork. So from there, once we have the distance from the target to the random, we scale our loss based on that calculated distance, and we update the weights for the sample subnetworks. And this, interestingly, produces the attacker's goal once he applies over any fox, and produces the stealthily poisoned super network. Right? So let's look at the application of VillainNet in the same kind of scenario that we had before. So this time the adversary chooses the VillainNet methodology instead of the traditional poisoning approach. So if we look at the graph, we can see that the orange points, which represent the attack success rate, show exactly what the attacker wanted, right? So only subnetworks with the lowest latency are affected by the attack, meaning that in the case of the car, which would be traveling the fastest using the smallest subnetwork, it would be affected. Right? And importantly, the attack success rate approaches 0 the farther you get from the target subnetworks. Also, this isn't just a single example, but you can kind of take this and apply it generically to whatever subnetwork you want. So this is when we apply it to the medium subnetwork, and then this is when we apply it to the maximum subnetwork. So for our evaluation, we evaluated on 2 state-of-the-art supernets, which were OFA ResNet and OFA MobileNet v3. And the data sets we used were C410 and BTSRB. We chose 6 latency configurations as our targets, right? And these, importantly, we saw that once we applied VillainNet, these target subnetworks had high attack success rate and high accuracy. Once we ran these, we wanted to also measure how these attacks affected other subnetworks once the attack occurred. So acting as an investigator, we said, okay, let's sample 3 arbitrary subnetworks. In this case, we chose minimum, medium, and maximum to see how those were affected as a result of the attack, right? So in the case of the tested subnetwork actually being the one that was attacked, we can see that the attack success rate and accuracy is both high, which is as intended. In the case that it was not targeted, we can see that the attack success rate is low and the accuracy is still high, which is also what the attacker would want to see. Finally, for intermediate latency targets, so stuff that wasn't our tested ones, we can see that all of them have low attack success rate, which is exactly what the attacker would want. So let's expand this kind of investigative scenario even further. So let's say if we sample 1,000 subnetworks out of that 10 to the 19, we can see that first, in a situation where the supernet was not poisoned at all, it has a baseline attack success rate kind of close to near guessing, which is 3.34%. So we evaluate using the 3 distance metrics that we had in the paper. You can find out more about those in there. And you can see that the average across the subnetworks is close to actually the baseline guessing, which means that the attack was very stealthy, right? So, and in the case of the attack, the target subnetwork also had high attack success rate, which is what we wanted. So importantly, the average across the 1,000 is the same, if not lower, or very close to the attack success rate for a non-poisoned supernetwork, but the targeted one still has very high attack success rate.
I just had one confusion. So the only reason that this works for SuperNet and not all neural nets is just that because in training you specify which are the subnets, right?
So the whole point of a supernet is you take a neural network and train it a single time, and you can use it for a wide number of deployment conditions. So let's say I was a smartphone manufacturer, right, and I had varying types of smartphones that had low power, high power, whatever, right? But I only wanted to train one neural network, right, to save cost. I can train a super network and then deploy various subnetworks to each of the phones, right, to save cost, instead of training however many types of models.
And why would this not translate to all kind of neural nets? Because people hypothesize that the backdoor path in normal neural nets is also very sparse. So
I'm confused about your question. You maybe rephrase?
Maybe I can take it offline, but I'll rephrase that. Whenever in a normal neural net, when you trigger a backdoor, So there has been like previous works which emphasize that not all the activations are activated in whenever you inference upon targeted sample. There's only a specific subnet which gets activated in a normal neural network as well. So
I think that you're confusing the definition of subnetwork here. The subnetwork is something that's actually defined by the system in this case.
Okay,
So
that's what
a normal neural network, you're just taking the whole network and running through. Whereas you're correct, there's certain neurons that might activate, right, corresponding to the backdoor. In this case, that's not kind of what we're talking about here.
Oh, okay.
Yeah.
Are there any other questions? I probably have one more question. Could you please go back to go back to this experiment? Three figures that showing the difference between the minimum subnetwork, median, and the maximum.
Yeah.
Could you please explain a little bit more about the difference between these three results?
Yeah, so in this case, the target of the attack was actually the minimum subnetwork, right? So you can see that the subnetworks that had the lowest flops or the lowest latency were affected, right? So in the case of the medium subnetwork, you can see that everything at the low end and everything at the high end had close to zero attack success rate. The stuff that was in the middle, so it might be, it's basically a medium speed subnetwork has the high attack success rate. And then the same thing for the large. So only the subnetworks that were the most expensive, right, have the attack. Does that make sense?
Yeah, it is. Thanks.
Thank you.
Okay.
Your result showed that 99% of the accuracy. Are you sure it's not overfitting?
Sorry, could you
It's
rephrase?
not happen overfitting in your model?
I think she's asking like success rate like very close to 1. Any chance you overfitting?
Yes. I mean, this is a very simple backdooring scenario. This is just merely whatever prior work has done. But yes, it's like if we're just using a simple trigger, it gets close to 99%. Yeah.
And I guess it's a white box setting, like you need to know the
Exactly. Yes. It is a white box.
Any more?
Yes. Is there any kind of link between how densely the subnets kind of congregate along this axis and like how pure your kind of attack success rate spike is?
Yeah, actually, we have a discussion of that in the appendix, and you can see that when you try, you can basically adjust the hyperparameter to make it more or less kind of spiky, right? And there comes a point where the training won't converge, right? So once you pick a hyperparameter that's too large, there's no way for it to be, like because of this inherent weight sharing, there's no way for just one subnetwork to be affected, right?
Okay, I guess that's all. Thank you very much.